Hello, everyone, and welcome to another wonderful day of industrial chemistry. So, today we're going to be talking about how we can take the unit processes and operations we learned about last time and combine them together into a neat, condensed way of showing what an entire industrial chemistry process looks like. And to do this, we're going to make up flow diagrams. And these are really the bread and butter of industrial chemistry. But before we do that, I want to go through a quick review of our chemical processes. So these include unit operations and processes that allow us to, in a net way, turn cheap feedstock into valuable products. So some of our unit processes can include biological reactions, most of which are going to occur in a fermenter. Cracking, so these tend to be high energy, high temperature processes that can break down organic molecules, such as long chain carbons, or ethane can dehydrogenate and turn into ethene. These often take place at very high temperatures. Polymerization, so turning ethene into polyethylene or other polymers, and we'll talk more about that later this semester. Or hydrolysis, our good old fashioned making of soap. Uh, However, we also have our unit operations. So these are physical manipulations, no chemical reactions involved. And these are old friends, things like mixing, size reduction or aggregation of building up size, heating and cooling, distillation, extractions, or vaporizations. So in these cases, we're often doing a lot of phase changes, physical manipulations, and temperature modifications. So these also require their own special equipment. But the problem is that in industry, I'm never doing just one of these. I often have to link many of these processes up together. So we need a logical and simple way to combine these unit processes and operations. And one of the easiest ways we can do is by drawing each one of these steps as a block. So I'm going to make a nice square and put the name of each step inside that square. And then I link these together with lines that, and over those lines describe all of the components in the chemical stream and the direction of flow of that stream. And so when I do this, I can combine multiple blocks together and build up an entire chemical process. Now, this is a little bit kind of obscure, so let's work through a real example. So here's a good and fairly simple one. Let's say I have air, and I want to go ahead and get a nice pure stream of nitrogen and oxygen, because it turns out both of these gases can be sold for a profit. And, they turn out to be useful in a lot of medical and chemical processes. But yeah, who cares about that? It's all about money. So one of the first things I'm going to do is I'm going to specify my incoming stream. So that's air. And then it's going to go through a unit operation. Specifically, I'm going to run it through a condenser. So this is going to typically pull out the least volatile components of air out. In this case, that would be water. And then what I'm left with is called dry air. So I have three chemical streams, one input, two outputs, and then I can specify each one of these outputs. And then that will go into the next unit operation, which is a filter. So this filter is going to be very fine, and it's going to essentially pull all of the bigger components. So that includes things like CO2 and a lot of our organic compounds. So this would be everything that smells, and all of that will get pulled out on the filter. Unfortunately, as I specified last time, the filter will often need to be removed fairly regularly. You can do some neat tricks so you can get these to come off as a gas instead of as particulates adsorbed to the filter. But what this leaves behind is just N2 and O2. So who doesn't love nitrogen and oxygen? However, typically you want these separate. For example, I may want pure oxygen for to use in medical ventilators, or I may want pure nitrogen to work in a safe inert environment for chemical operations. So the next thing I'm going to do is run these through a cooling unit. And what you'll notice is I'm going to have the same input stream as output stream, because the only thing that changed in this case is temperature. So you may note we might need a little bit more information on this specific block diagram. And then I'm going to run these through a distillation apparatus. And this will essentially separate O2 and N2 based on their boiling points. So I'll get a nice unique stream of nitrogen and oxygen. And it turns out this is exactly how you get nitrogen and oxygen for industrial use, is by essentially running it through this same general process. But may notice that this is kind of the bare bones technique. It doesn't contain nearly as much information as I would like, and it doesn't exactly pop to the eye. So while block diagrams are very easy for me to do on a computer with no special software, and who doesn't love that, we often need something a little bit more descriptive. And so what we can do is replace all of those blocks with descriptive symbols. So one of the things to watch out for is there is a lot of symbols to use. And so here on the left, I have a quick description of several common symbols. You may notice that there is no unit operations in this list. It's so far just unit processes, but includes things like valves, which are often depicted with this hourglass shape, an extra D on top of it essentially makes it a control valve, which is going to mean that these are the ones that can be manually controlled. One of the ones you're going to run into fairly commonly is going to be this more jagged symbol, which is a classic example of a heat exchanger. So this is one of the more common symbols, but there is often several other ones you can use. And another one that is always a good favorite is columns. So so columns are often represented by these vertical ovals. However, you can also find very similar symbols for these are often used for distillation columns, which is something that, as I said, distillation is really a bread and butter technique of industrial chemistry. So one of the nice things about these symbols is once you get used to them, they provide a lot of extra input very quickly, because I can simply look at a symbol and know exactly what type of unit operation or unit process I'm performing. It also gives a lot of information about where the inputs are coming in and where the outputs are leaving. So understanding flow diagrams is one of the more useful things you can do. However, it is worth noting that there is a lot of extra software programs and libraries which can really help making these diagrams, including several essentially CAD programs, which will provide symbols that you can copy and paste in. But for most of our purposes, we're going to tend to use more simple libraries where I can just look up the symbol needed. And again, the software programs making these can be fairly useful. Now, let's go ahead and take that same exact production of nitrogen and oxygen from raw air and do this in a process flow diagram instead of a block diagram. So in this context, I still have an air input, but now it runs into a condenser, which is going to be the trapezoid shape, where we have water coming off the bottom of the condenser, whereas dry air flows through. So again, the shape can actually tell you a lot about which stream is leaving in which manner. Then we end up running that through a filter, which is given by the oval shape, where CO2 and the organic carbons are going to be, again, leaving as the solids. And then we have a heat exchanger, so this is going to be our cooling unit, running through a fractional distillation column, you can tell that it's fractional distillation by the addition of plates. Occasionally, but rarely, you can actually show exactly how many plates are involved and what plate the input enters simply using the pictorial diagram, though most don't actually offer that much detail. And in this case, we can also see that N2 is going to be our top or more volatile component, and O2 is going to be our less. So one of the great parts is that just using these two simple ideas of either block diagrams or flow diagrams, I can essentially model or give a pictorial description of almost any industrial chemical process you can imagine. However, it's worth noting that most chemical processes tend to follow a general motif. I'm going to be inputting a raw storage material, which I'm then going to have to prepare in some fashion. This can be things like I need to reduce the size, I may need to cool it, I may need to separate it. And it's worth noting that this second stage may constitute of several parts. And in fact, sometimes we don't ever get past stage 2, as we just showed, where we had no reactions or unit processes. But this is often a very important factor because we need to prepare our reactants for a net reaction. And then inevitably, with most reactions, we have the product we want, but we also have unreacted materials. And as I'm going to show you later, one of the biggest tricks of having an overall process with high efficiencies, even when the reactions themselves can be quite inefficient, is going to be recycling unwanted materials. So it will keep going around until eventually it forms product. However, we don't always have just the product we want. We often have byproducts and wastes. So byproducts are going to be something else that I might be able to sell. Waste is, well, more unfortunate. One of the big things you'll want to try and do is minimize waste and maximize end byproducts. And because it turns out that most of your product is still unpure, you'll need to go through a second set of product purification. So this is after having removed any byproducts so that it can be prepared for storage. And then after that, send it off to somebody else who's hopefully paying you for it. And again, one of the things I do want to emphasize is not all of these steps are going to be present for every chemical system. So for example, sometimes we're just stage 1 and stage 2 because there's no chemical reaction. Sometimes there's no chemical byproducts. Sometimes I don't have a recycle line. And very, very rarely, we can also even minimize wastes. So one of the things you should always kind of watch out for, we may end up skipping straight past stage 2 and 3, straight to purification and storage, or sometimes we'll skip these and focus just on prep. So, and again, watch out, many of these steps can be broken down further. For example, I may have to have a size reduction, a filtration, and a cooling cycle all involved in prep. So, while this overall scheme is fairly universal, there's a lot of complexity in the details. But one of the other things that we've already seen a little bit today is that it turns out that I may need a little bit more information besides just what is present in each of these feed streams. So next time, we're going to be talking about a little bit more about exactly what sort of detail I might want to provide on what is present in each of these feed streams between my individual unit operations and processes. Until then, take care, stay safe.